Okay, so all right. The last class we talked about the exponential mechanism. And some meta properties, right? Exponential mechanism, we said, sometimes you might not be interested just in like a numerical value. You might be optimizing or something. What is the best, most common disease? What is the best utility I can get, and something like that. And you should think of it as essentially private release for argmax. Okay. Then we also discussed some meta properties of differential privacy. And today, what we're going to do is talk about a relaxation of differential privacy called approximate differential privacy. And then we'll see one more mechanism called the Gaussian mechanism. Right? So Laplacian mechanism, exponential mechanism, and Gaussian mechanism, these three are pretty much the mainstays in differential privacy. And then I'll say a few words about private machine learning. And oops, sorry, I should say, first I'll discuss advanced composition, and then about highway. Okay, so these are the things that we're going to target. And reminder, assignment 3 is due today. At 10 p.m. Right? Okay. So we saw, this exponential mechanism, which can give us something as, it gives us privacy. At the same time, it gives us utility, which is close in a quantifiable way to the optimal possible value. All right. And okay. So far, what we've been discussing actually corresponds to what is known as pure differential privacy. Okay. So what do we mean by pure? Recall the guarantee that we had, right? Epsilon differential privacy meant that for any two neighboring databases, we had a very nice guarantee. For any possible outcome, now this is great guarantee, pretty much even rare events, their privacy is protected, but sometimes this is a bit too much to hope for. When we can have epsilon differential privacy, of course you should do it. Like for instance, if you're computing the mean or median or anything like that, if you have a low sensitivity function, we know how to get pure differential privacy without too much cost. Okay, but as an example, what if we had an extremely rare event? Right, so it's so rare that you're probably never going to see it. But so this would imply that for any neighboring database, your mechanism needs to satisfy something similar. right? So you have to deal with even numbers which are as small as 2 to the minus 100, and even then you need to have this multiplicative guarantee. So the approximate differential privacy kind of relaxes this constraint a little bit. So what would you think would be a nice way to relax the pure differential privacy to something still reasonable, but perhaps easier? Any suggestions? Yeah?
Portion of your thing out, but you're allowed to have like one or two situations.
Right. So, I mean, I think essentially what you're saying is if the event is very, very unlikely, maybe don't care so much. Right. And this could be in terms of like individual items. So we will say we will say a mechanism M as before is epsilon delta differentially private. Okay, so now we have two parameters, epsilon, which kind of controls the multiplicative deviation, and delta, which controls kind of how small should an event be for you to care. Okay, things which are very unlikely, I don't care. As long as they're still unlikely. I don't want unlikely events to become likely when I just change a single user. But if it's 2 to the minus 100, I don't care, for the neighboring database if it is 2 to the minus 50. Multiplicatively, the gap is big, but those are two very small numbers, so I shouldn't care much. Okay. So one kind of slick way to formalize that is to say for every possible outcome y and any two neighboring databases, you sort of have the same multiplicative guarantee as before. Okay, but you're also allowed an additive error. So if things are very unlikely, I don't care about that, as long as the new event is also somewhat unlikely. All right. As an example, if epsilon equals 0.1, or actually, let me just say 0.1, then under pure differential privacy, what you'll have is e to the minus 0.1 times this. Okay, so this is what we'll have under pure differential privacy. Right? And for us, it would be something like this. You are allowed this additive delta for any event. Okay. So essentially, you should get the multiplicative guarantee for things which are more likely than delta. Otherwise, you don't need multiplicative guarantee, just additive approximation. Yeah.
Just the person idea here is that delta doesn't depend on that. Also, it's like a constant bound on how loose.
So actually, that's a very nice question. So kind of what range are we thinking of? Right, epsilon we should think of as like 0.1 or 0.01. That's a reasonable thing. But delta, as let me just discuss, we should expect or we need it really to be very small. Okay, so let's just since you brought it up, let's do a thought experiment, right? So intuitively, I think one way to interpret this epsilon delta differential privacy condition is we have the usual privacy in some sense, except with probability delta. With probability delta, you can do arbitrary stuff that still satisfies epsilon delta. Okay. So for instance, imagine as a really trivial example, but kind of to illustrate the difference, you'll say, okay, so let's say I do something like this, the mechanism does something silly in the following sense. With probability 1 minus delta, E output jump. Okay, no matter what database you see, with probability 1 minus delta, I'm just going to output random values, nothing to do with the database. All right. On the other hand, with probability delta, I'm going to output the entire database as it is. All right. Okay. So either I output junk most of the time, but sometimes I output entire database. Does this satisfy epsilon delta differential privacy? Yes, in fact, it satisfies 0 delta differential privacy, right? Because most of the time you have the exact same probability for 2 neighboring databases, but with probability delta, you just get the entire database and the values would be different. Okay, does it make sense?
That we have epsilon 0 differential.
No. So this is essentially 0, 2 delta differentially private. Okay. But it does seem like it's not very good, right? So you cannot take delta to be like 0.1. It has to be much, much smaller. Right? So we're happy in terms of privacy when epsilon is like 0.1, but for delta, we need it to be much, much. Okay. Kind of further understand this, let's look at another example. Well, okay, so let me just write a couple of equations why this is, right? So what's the chance that the output is X in the first case that is actually delta? Right? And what's the chance here? It's probably 0. Right? So basically, multiplicatively, the gap is like humongous, but additively, the gap is delta. So that's the reason why it satisfies 0 delta differential. Okay. And anything which is not X or X prime, because it's junk, both of them happen with essentially the same problem. Yeah. Or let me say almost 0. Because the only, so you either output the entire database. Maybe, okay, let's say you output something like this. Yeah. All right. So now you only output the entire database with probability delta, but X and X prime are different in one coordinate, right? So will you ever see X prime? No. Will you ever see X? So what are the possible outputs? You'll either see perp or basically bottom, or you will see X prime. Right? So this is 0, whereas there it is delta. Okay. And how about the probability that M of X equals bottom? That is 1 minus delta, and that's the same under X prime 2. Right? So most of the time, the chance is exactly the same. So you cannot tell which database you got the answer from if you see perp, or otherwise you'll see the entire thing. Okay. When you do the perp, you actually get 0 delta, so it's fine. Okay. Now, that seems like a trivial example, but you can also think of something maybe just a little bit more thoughtful. So let's say I do something like this, to get privacy, I say for each person, with probability 1 minus delta, I replace their record with junk, right? Really just bottom. Okay. With probability 1 minus delta for each person, I just replace their record with junk. And with probability delta, I keep their record. Okay. And now, once again, this is going to be, you do this sort of data sanitization. I take in my database for each person, I do this sort of coin flipping, probability 1 minus delta, I throw away their record with probability delta, I keep it. Okay. And then I'm going to do whatever algorithm that I had before on this new database. All right. And then run whatever algorithm you wanted to on the new database. Okay. So what kind of privacy would this have? Any guesses? So for each person, I'm just going to throw it away with probability 1 minus delta, keep it with delta, and then do whatever algorithm that you had before. Yeah. What kind of privacy do you think this will have? Yeah. It is similar to the previous one, right? If you take two neighboring databases. So let's say I take two neighboring databases, X and X prime. Right? So everything is the same except, maybe here you have the different entries, right? So with probability 1 minus delta, basically these will be thrown out, right? So essentially you will get approximate okay. So you'll essentially get 0.2 delta approximately. Yeah. It's actually 1 minus delta whole square, right? That's the chance. And then that's basically, the complement of that is 2 delta plus minus delta square, which are relaxed to 2 delta. All right. So in some sense, it's easy to get approximate differential privacy. So, but on the other hand, if you think of this setup, it doesn't seem that private, right? Because I'm not putting any constraint on what algorithm I use afterwards. Maybe it's releasing the entire database. Maybe it's just outputting the names of the database after I do this pre-processing, right? Which seems pretty bad, but it's somewhat okay because if you think about it, on average, how many users' records actually go through? Imagine I do this pre-processing. I start from my original database. And each one somehow, maybe the first one became junk, the second one survived, the third one became junk, fourth one became junk, and so on. How many do you expect on average to survive? Yeah. Exactly, right. So essentially, the number of records that survive is roughly delta times n, right? So as long as for this to give a meaningful guarantee on privacy, we should think of delta as being much, much less than 1 over. Okay. So if delta is like 1 over n squared, it's not too bad, right? Because on average, we do not expect even a single record to survive. Obviously, this would be the utility of such a mechanism would be terrible. But in terms of privacy, it kind of at least makes sense. You're not leaking any records, or at least it's very unlikely that you would leak records. Okay. For the most part, we should think of epsilon as being like 0.01 or 0.1, but delta should be like 1 over n squared, 1 over n cubed, or essentially something like 1 over n. Okay. And most of the time, we want the dependency on the number of users to be like logarithmic in 1 over delta. And you can be polynomially dependent on epsilon, but your dependence on delta should be really good. Okay. All right. Now, okay, that's fine. Now, where can we get epsilon delta differential privacy from? Why study it? Well, it turns out that if you want epsilon delta differential privacy, then you can do better than for pure differential privacy, at least in some cases. All right. So the punchline is we relax the notion of privacy, but do we gain something from it? Right? That's it. I mean, that was the whole point. We wanted to relax it so that to get something still meaningful, but perhaps we had to pay less in terms of the price of privacy. Okay. Do we gain anything by going to? Okay. And I want to iterate this sort of conceptual thing that you should keep in mind, right? So when someone says, okay, what's the price of privacy, or you're trying to do something differentially privately, you should think of it as really, we have two things, right? The privacy parameters, epsilon, delta, dp, or maybe if you're interested in pure differential privacy, it's something like this. You have some accuracy target, alpha. Okay. And then the question is, how large should n be to satisfy these? Okay. How many data samples do you need if I want to get accuracy alpha and satisfy this privacy gap? Right. So statistical machine learning basically tells us how to answer this question. For various function classes, let's say I give you linear regression and I tell you I want accuracy alpha. How many measurements do you need? How many examples do I need? We know that exactly, right? And now, maybe for computing the mean, if you want accuracy alpha, how many samples do I need? How many survey questions do I need? We know all of those things, from hundreds of years ago, right? And now we are asking kind of something similar, but the price of privacy. If I want these in addition, how big does the database have to be? Okay. Ideally, you want all of these things to kind of play well. So ideal is n is cost without num required without privacy times maybe your sample complexity requirements, how big a database you need increases because you're looking for private things now, private learning or private way to answer the queries, but you want the dependence to be kind of log poly in log 1 over delta, and you can have polynomial dependence on it, right? As I said, we think of epsilon as being like 0.01, whereas delta is like 1 over n to the 3 or n to the 10 or something. Okay, just keep this in your back of your mind. That's kind of the ideal ballpark, and what you get will vary across different mechanisms and different problems. Okay. So for getting pure differential privacy, we saw this global technique, right? We saw how to get pure differential privacy from sensitivity, right? In particular, from sensitivity in the L1 norm, which was something like so if I had a function with k possible outputs, which had bounded L1 sensitivity, then I can get epsilon differential privacy by doing the Laplacian mechanism, right? And it turns out for approximate differential privacy, you can do something similar, but under a weaker requirement on sensitivity. Okay, so we're going to show that you can get approximate differential privacy for functions under a weaker notion of sensitivity. And what is this weaker notion of sensitivity? This is basically L2 sensitivity. Okay. So for instance, let's say I have a function which outputs k values. Then the L2 sensitivity is take the max difference over any two neighboring databases of the L2 norm of the difference between the two possible outputs. All right. So this is basically right. So the previous sensitivity was L1 sensitivity, S1 of f, meaning you're looking at sum of absolute values. Now we are looking at the root mean squared of the differences. Okay. And so to understand, why this is better, let's go back to sort of the basic example that we looked at, but in a more general case. Okay, suppose I have a database which has n users, okay, and each user's record is a vector in 0, 1 to the d. Right, so there are d features, and each user's record has 0 or 1 values for each of these features. Maybe you're looking at d attributes. Does this person have high blood pressure? Is he above 60? What's the is he a smoker? Did they have surgery before? All of these things, binary things for now. They don't even have to be binary. I'm just taking this as an example. You can take anything numerical too. And the function that we're interested in computing is just the average. Okay. Makes sense? I'm just interested in computing the average value of these things. If I want to release this information differentially privately. If you want pure differential privacy, one way to do it is to look at something like Laplacian mechanism, right? So if I do Laplacian mechanism, then I get S1 of f, which is max of x comma x prime. So what is the max value that you would get? Any guesses? If I change one user's record, how much can the L1 norm of the two things differ? Yeah.
Possible for each feature to get flipped, so it'd be times number.
Exactly, right? So it could, I mean, this is only 0 or 1, so the gap is like 1 at most. So d over n. Right? If it's one-dimensional, when we're computing the plain mean of numbers, essentially we said, okay, if I flip one guy, one coordinate here, then it changes by at most 1. But we have d coordinates. So flipping a user can change the function output by d over n. So if you have a very high dimensional data set, then the sensitivity is pretty big here. Okay. And how about L2 sensitivity? Any guesses? Yeah. Yeah, exactly. So you get square root of d divided by. Okay. So why is that? Well, let's think of this, right? F of x is 1 over n times summation I equals 1 through n xi. So let me write this as x1 plus x2 plus xn minus 1 plus xn. And f of x prime is essentially the same thing, but the last coordinate or last user's data has been flipped. Okay, so these two are no longer the same. Okay, so that means f of x minus f of x prime, when you compute it, everything goes out and is just xn minus xn1. Okay. And since the entries here are between 1 and minus 1, the L2 norm of this vector is at most square root d. Right? So even if d is like n now, you still have sensitivity which is lit low of 1. Right? If you think of a high dimensional data set, the gap between these two is very big. Okay. So potentially, you could design better algorithms if you had something which works with L2 sensitivity instead of L1 sensitivity. Okay. All right. So with that in mind, let's now design a mechanism which only requires the L2 sensitivity to be small. Okay. Laplacian mechanism doesn't work this way. It really requires L1 sensitivity. And the way to do this comes from what's called the Gaussian mechanism. Any guesses as to what it might be? And just do some, yeah? Exactly, right? It's kind of in the name. Instead of adding Laplacian noise, we're going to add Gaussian noise. Okay. So, I mean, we'll see why that's better for this kind of setting. So we have a function f, right? And we are going to sample z1, z2, so on up to zk that are IID n0 sigma squared, right? So in Laplacian mechanism, we computed the function and added some Laplacian noise, right? So here we're going to compute the function as before, but then add Gaussian noise, okay? With some variance, we had a parameter in For variance in the Laplacian case, we have something similar here. We'll see what it needs to be to get privacy. And output f of x plus c1, c2. Okay. All right. And it turns out we can show a generic theorem about the privacy that you would get for Gaussian mechanism. And the only thing that you need is L2 sensitivity. So we have a function let me just say Gaussian mechanism with, so how much noise do you need to add? Your noise needs to be something like this. Okay. So for Laplacian mechanism, we just said, okay, you need the parameter b to be S1 of f divided by epsilon. Okay. Something similar here, but you have something on delta too. So as long as the variance is at least this much, is epsilon delta differentially private. Okay, yeah. 1.25, yeah.
Like a magic number.
Not really. I mean, I just wrote it down for like, being very precise. It just comes out when you do look at the actual calculations of working with the PDF density. I mean, it's even probably a simplification. It has some pi in there. Okay. Yeah. So where does this come from, right? So it comes from the fact that, I mean, as think of it really as square root log 1 over delta times S2 of f. Okay. So instead of going S1 of f divided by epsilon, you're going to S2, but you're paying a penalty, which is the square root log. Okay. Yeah. Sorry, say that again. Sort of. I mean, it's kind of implicit in our assumption about we're assuming that you normalized it somehow when we are doing this S2 of f. Right. So you should, before computing S2 of f, you should kind of, normalize things already. Okay, does it make sense? We're pushing it into the function itself rather than in the noise, just so that things look more uniform when you're adding the noise. Okay, that's a good question. We'll come, I mean, when we talk about doing things like this for like ML, we'll see you have to do something. Okay. Any other questions? Okay. All right. So we're not going to prove this theorem just because, it's essentially follows from, just working with the PDF of the Gaussian distribution. It's not complicated, but you have to use the PDF formula and do some manipulations, and you will get it. Okay. But I want to kind of see what this gives us for various questions. So as an example, let's compare Laplacian versus Gaussian for mean computation. Okay, so the mean example that we saw here, right? We said S1 is like d over n, S2 is square root d over n, right? So if you want to do this, to get epsilon pure differential privacy, for F, we need Laplacian noise with something like S1 of F divided by epsilon, right? So that is Laplacian of d over n times epsilon. Okay. Now, what does this mean? Essentially, it means that you're computing. So we compute f of x, right? And add noise. That is how much approximating each coordinate, how big or small is the noise. Laplacian, we said the chance that t times the variance is kind of decaying exponentially with t. So typically it's about d over n times epsilon. Okay. So we are adding this much noise to each coordinate. Okay. And on the other hand, to get epsilon delta differential privacy, we need a Gaussian mechanism with this much noise. Okay, so we need Gaussian with sigma equals it's square root d divided by n times epsilon, right? So meaning we compute f of x and add noise that is typically about square root ln 1 over delta times square root d divided by n times epsilon. Okay. So the savings in the noise that you're adding is pretty big if you have high dimensional data set. Low dimensions, it doesn't matter. In fact, probably this is worse, but in high dimensions, this is much better. Right? So in particular, if we want accuracy alpha in each coordinate, then for epsilon dp, we need n to be roughly d over epsilon times alpha, right? Because we want the noise to be less than or equal to alpha. So it needs to be, the database has to be like d over epsilon, right? Whereas for epsilon delta differential privacy, you need n to be something like Okay. So the requirement on the data set size is improving almost quadratically from going from pure to approximate differential privacy. And this is not just for mean, it also happens for many other important functions. Okay. Does this make sense? Why this is kind of a nice thing to do? All right. Okay. And so if there are no other questions about Gaussian mechanism, let me pause for, let us take a break for 5 minutes. And when we come back, we're going to see how approximate differential privacy is actually helpful for something completely unexpected. Okay, this is for composition. You can do something better from approximate differential privacy than with pure differential privacy. Okay. All right, let's take a 5-minute break, and when we come back, we'll talk about that. Okay. So now that we have this epsilon delta differential privacy, and we see that you can do better, almost quadratically better if you want epsilon delta differential privacy, even for a basic primitive like mean computation. Let me talk about another direction in which the approximation really makes a big difference, like similarly quadratic improvement. And this is in the context of group privacy once again. Group privacy and composition. Okay, so first, suppose we have X and X prime are two databases that differ in k rows. If I have two databases that differ in k rows, then we said earlier that you still get some kind of privacy, except that the multiplicative thing, instead of being e to the epsilon, became e to the k times epsilon. Okay. And something similar is true for epsilon delta differential privacy too. You get like e to the k times epsilon times probability m of x prime equals y. Okay, so this part is fine. And then you get an additive term, which is like k times delta. Okay, so this is what you get. So for instance, recall for pure differential privacy, we had if we have pure differential privacy, we just get a multiplicative e to the k times epsilon. And in this case, you get e to the k times epsilon plus something which goes with delta. It seems natural enough. You just have to work through the equations iteratively, and you'll get this bound. Okay, but that's just for good to know. But I don't think that's as interesting as what happens for composition. Okay. Now, recall what we discussed many lectures ago. We said, suppose we had M1 up to MK, epsilon differentially private. Okay. Now, if I do them one after the other, then their composition okay, this, yeah.
Delta is independent. It's like the exponential.
You mean this e to the k times epsilon? Yeah, it comes up because, the first time you do, you'll get e to the epsilon plus delta, right? And then the next time you'll get e to the epsilon times that.
That versus the delta.
Mhm.
That
Not too much, because typically we think of delta as being reasonably small, right? So you're definitely right that, like once, this starts becoming very bad once k is like more than 1 over epsilon, right? Because you have something, until k is like 1 over epsilon, this is something a constant, so it's okay. But if k is becoming more than 1 over epsilon, even this is getting pretty bad, right? So it's getting worse, but it's also getting worse there. So, it's not hurting in particular just because of this. Okay. Right. And so for pure differential privacy, you can have, there's this composition theorem, right? Now imagine you have a database, you ask it to, tell me what is the average of all of the people in the United States. You have census bureau, I go and say, okay, tell me what's the average age of all of the people in the United States, right? So that's my first query. And then based on the answer that I get, I ask, okay, tell me what's the age within California or within Texas, or tell me how many people are kind of, earning somewhere or something like that. The questions are dependent on each other. Okay. So that's what we mean by composition here. Like, you should think of M1, M2, and so on, kind of as dependent on the answers that you got from the previous round. Okay, I'm asking adaptive questions. I ask something, based on that answer, I decide which question to ask, and based on that, I decide which question to ask, and so on. Okay. So if that's what I'm doing, then you still get privacy, but it kind of goes down as this k times epsilon. Yeah.
A little bit of counterintuitive, because the multiplicative pattern happens when you are having like independent. Saying that you're adaptive. Right?
Yes, essentially like a union bound. You basically, instead of saying e to the epsilon hit in the probability, you get e to the k times epsilon.
Better than that.
Not for pure differential privacy, actually. Okay. There's definitely an upper bound, and you might wonder if we can do better, but it turns out you cannot for pure differential privacy, but for approximate, you can do it. Okay, we'll see. Okay. All right. So this is called, okay, so this is for pure differential privacy. And I said, this follows from kind of applying the law that, okay, you have probability, mk of x equals y is less than or equal to e to the epsilon times probability, mk of x prime equals y. Okay. And then you do the same thing again, probability mk minus 1 . So you can show this and then so on. Okay, so that's how you get this e to the k times epsilon, much like, kind of, group privacy, but you're composing things. All right. Okay, so that part is fine, but now you can work with something similar for epsilon delta differential privacy. And this is called the basic composition theorem. If I have these things which are individually epsilon delta differentially private, and you have adaptive queries. So again, remember, we're making adaptive queries, meaning, okay, tell me how many people are there in California, right? And based on that, I'll decide what to do next and so on, okay? Then their composition is K epsilon, K delta differentially private, all right? So kind of the same thing. You have K epsilon differential privacy here. You get K epsilon, K delta. It makes sense. This is basic composition theorem in the sense that you just have to apply the same law again and again. You will get this. Okay. But the punchline really comes in a different setting. There's something called the advanced composition theorem. Right? What does the advanced composition theorem say? Well, if I have K pure differentially private mechanisms, okay, I'm starting with pure differentially private ones. Okay. Then their composition is something like okay. So as long as epsilon. So think of epsilon as being something which is less than 1. Then it's saying when you do the composition, if I wanted pure differential privacy, I'm paying something like K times epsilon. Okay. But if I'm willing to go to approximate, I essentially pay square root K times epsilon. Okay, this is the dominating thing essentially. Okay, so really think of this as square root K ln 1 over delta times epsilon common delta. Okay, so in other words, to get non-trivial privacy for the composition, we need epsilon to be something like 1 over square root. Or in other words, you can say you need K to be like 1%. Okay, so as long as K is like, maybe substantially less than 1 over epsilon squared, you still get some non-trivial or useful privacy guarantee. Okay, whereas if I use the basic composition theorem, you need, so this is kind of useful when K is like, less than or equal to 1 over epsilon. Okay, so in some sense, the advanced composition theorem allows you to make quadratically more adaptive queries without paying in the privacy. Okay, so imagine starting out with epsilon is like 0.1. Okay, if I started out with epsilon is being 0.1, then under basic composition, I can only make 10 queries before the privacy guarantee sort of starts becoming trivial or not that useful. Okay. Whereas with the advanced composition, I can make 100 queries, 100 adaptive queries. Okay. So advanced composition allows us to make quadratically more queries. It's kind of a non-trivial theorem to prove. You're paying something because you're not getting pure differential privacy, even though you're starting with pure differential privacy and going pure to approximate, but I'm now, allowing myself to make way more queries. Okay. Yeah.
A priori, like,
You could, but it's not going to help you as much. The main thing is that adaptive queries are kind of nasty to handle. In fact, people have found that many times in scientific fields, people do this mistake, right? You have the same database, okay? And then they start doing p-values and so on, like in some biotechnology or biology or somewhere. And then at some point, they're using the same database again and again by making adaptive queries, and you end up overfitting a lot. Okay. So, like when you're making adaptive queries, so let's say you're trying to do a double-blind study for something, right? So the underlying principle behind this is that you have a population of all people, and I sample 100 people at random, and I'm then checking whether or not my drug worked on, right? Okay, but now let's say I do the first test, and I say, okay, among all those people on which this test was successful, on that sample, I do something else. The second sample is not at all random now, right? It can be very biased, right? So that's adaptive query really distorts the truth. And this has led to many sort of erroneous studies, which have had huge sort of detrimental effects too. Because people don't realize that how many adaptive queries you can make really degrades. Okay. If I'm making sort of adaptive sort of studies, then the size of the starting population needs to be much bigger than if I'm doing sort of independent studies. Okay. And the same thing kind of should have happened here, that if I'm doing this adaptive queries, then I should only be able to do something like 1 over epsilon. But with this advanced composition, I can do quadratically. Okay. And in fact, this idea of advanced composition has been exploited in applications which have nothing to do with privacy. Right? So as applications, so the first application is if you have participated in some sort of machine learning contests, there'll be something called the leaderboard. Do you know what a leaderboard is? Like, let's say you're participating in a Kaggle competition, right? So what happens there is, you have some data set that is released to you. That's a training data set. And then there is an evaluation data set, and then there's a separate sort of test data set. So there are 3 pieces. So let's say Kaggle or other ML competitions. So there's a training data set. Released for everybody. And then there is an evaluation, which is also hidden for you. And then there is the actual test data set. Okay. So meaning what you do is you use this data set to build your ML model. Okay. and you submit your model to the server, it evaluates it. This evaluation data set is also hidden from you. And then you get a score. Right? And then there's a leaderboard. It tells you, okay, you know, which team is kind of leading. You know, top team, second place, and so on. Okay, so the leaderboard keeps changing. At the end of the competition, you know, you just go to the test data set and you get an evaluation. All right. And what people found is for some competitions, just by making these queries, you know, you can, you know, some clever hacker, what they found was, I'm not even going to look at the training data set at all. I'm just going to submit various ML models, and based on the scores that I get, okay, just submit various models. Based on the scores, submit a model which got 100% score. Which is, they did this without looking at the training data set at all. They're not doing any learning, right? Someone is telling me, okay, if I submit this answers, this model, your score is 50%. Okay, and then okay, if I submit this model, I get score which is 70%. By asking a few of these questions, suddenly you're saying here's a model which will get 100% accuracy. And in the entire place, I've never done any learning because I didn't even look at the training data set. The only thing that you're doing is basically figured out that whatever the scoring mechanism that they have is not very good. Okay. And this was a problem for leaderboards. And how do you maintain a leaderboard in a meaningful way without people hacking it out so that you're the leader without learning anything? Right. And a very nice process was suggested based on adding noise to the scores. Okay, so this comes from a paper called A Reliable Leaderboard for Machine Learning Competitions. There's a paper which did this. So basically it said, you know, if your Kaggle, someone presents you a model, you should not release the actual score that they get. Release the actual score with some noise. I mean, you're not trying to protect you're kind of trying to protect the privacy in the sense that you don't want this to leak. If the evaluation data set somehow leaks out, then you're in deep trouble because someone can just get perfect score there, right? So even though it doesn't look like there's any privacy necessity here, you can use it to mitigate other problems. Okay, it's kind of a very cool application, which, you know, is now implemented within various machine learning competitions. They actually do this when they're doing the scoring. Okay. And the other application is to reusing data sets in scientific studies. Yeah, which is basically what I said, you know, in fact, during for many trials during, I think, for the COVID vaccines and so on, usually when you do, like, let's say you're trying out a drug, you have a control group, you have a test group, right? You know, one group gets a placebo, one group gets a real thing, and then you're trying to compare how they're both perform, right? But now if you're trying to try 100 drugs, you really do need 100 control groups and 100 test groups. They all have to be different. Okay. Technically, because the control group is only getting placebo across all of these 100 drugs, you could think, okay, maybe I can use the same control group for all of these 100 different drugs. Right? It doesn't seem to violate anything biological. And I'm just giving the same placebo tablet to each control group. Why can't I use the same control group across the different drug trials? Okay. But the problem is then you end up with this sort of overfitting, based on how the results I got from the first control group, first test, first drug. I know something about the control group now. It's no longer independent for the second drug. Right. So that creates a problem, and people have been using, or at least trying to use, this sort of perturbation techniques to mitigate that. Okay. I mean, that's kind of a very high level overview, but at least hopefully it makes some sense of kind of issues you're facing. All right. Okay. So that's what I wanted to say about the advanced composition theorem. The proof of that, unfortunately, is not like, overly complicated, but it is involved. You essentially have to use some kind of martingale tail bounds. What saves you is you have this multiplicative e to the epsilon here, but it's not always multiplicative e to the epsilon. That's an upper bound. Typically, the expectation of the multiplication should be 0. And you can exploit that somehow. So instead of adding k different things, you can set it up so that you're adding k independent random variables. And if you add k independent random variables, it means 0. You should expect to be like square root k instead of k. Okay, so that's kind of the punchline, but the proof is a bit involved, so we're not going to go into it. Okay. Any questions about this? Yeah.
Same pattern problem.
Mm-hmm.
It's the data, right?
You mean release the query or?
On the,
Yeah.
but in doing so, variance.
I mean, okay, maybe think of it this way, right? So even if you work with unnormalized data, it's basically how much noise is okay in each coordinate, right? So if you go back here, if it was this, yeah, something like here, right? So I could potentially add more noise in coordinates where the variance is high, right? That's fine, because when I add the noise, the accuracy gets, add more noise, the accuracy gets hit, but my values are very big, then it's okay for me, right? So if my true value is like 1, a noise of 0.1 is okay. The true value is like 10, maybe a noise of 1 is also okay, right? So it's basically whether you scale the noise or scale the value should affect the accuracy kind of the same way, right? Like if one coordinate is always 10, one coordinate is 1, you technically should be adding more noise in the first coordinate, right? Because it's not going to hurt the accuracy at the same level. Instead, a better way to do it is kind of just normalize everything so that each coordinate maybe has same variance, and then do something. Okay. It's kind of implicit in our assumption that these entries are between 0 and 1. Okay, so each coordinate has the same range, but what do you do if otherwise? Then you have to do some clipping or normalization and then do the noise. Okay. All right. Okay. So that's about advanced composition. And the last thing I want to discuss about privacy is, so far we've been thinking of differential privacy from the context of, okay, somebody has a database, I want to make some queries to the database, I want to learn something from it without leaking too much information about the model, about the data set. Okay. But you might wonder, there is private machine learning. Okay. So what is the, what did we think of machine learning, right? So now when we say ML, think of what the many things that we did before. Maybe I have like user one. I have the data of all of the users. Okay. I use, it's with some curator. And like, let's say you're Google, right? You have billions of labeled images, I have a lot of email data. I built my large language model on it. Okay. And then I release the model to the public. Okay, I'm releasing the entire model, right? Model is a huge one. It could be all weights in my network, the architecture, everything, right? Okay, so all of this could depend on the database. But now if you look at this model, it might be leaking information about the users, right? In fact, this is not a theoretical scenario. People found that at least for some earlier models, by querying them appropriately, you could actually find out like some social security number of a user. Because you're just training the entire model on something. There's nothing which a priori tells us that this model weights did not memorize some information. How do you know it did not memorize, like, someone very important, like President Biden's, whatever, house address or whatever, something, someone importance data explicitly is encoded in the weights. Okay. In fact, there's a funny cartoon in XKCD, right? And the autocomplete just tells you where it's going to happen, right? Can you imagine, this is not a theoretical issue. You can easily imagine this happening, right? When you train predictive models on input from users, it can leak information in unexpected ways. Most recently, I think a month ago, someone found out that you can query ChatGPT so that it releases entire, like the history of user queries for some users. Right? There was kind of a bug in the interface, but based on the prompts, you were just learning the entire sequence of prompts. Okay. And so how do you handle such scenarios? How can you mitigate this? Well, if I want to take a principled approach at a high level, we don't want to get into the nitty-gritty details. I want to do something at a high level in the sense that it should be broadly useful. I don't want to, say, okay, here's something that will work. If I'm training a CNN with like exactly 100 nodes in the first level and 25 nodes, the filter size is this approach will work. Right? But then if you just change something, it might not be up, right? You want something like at least a formalization which is broadly useful. So what is one way to try and do it? Any suggestions? Yeah? Sorry, say it again. Yeah, so add noise to the weights is what you want to do. But to do that, that's a good suggestion. So let's say add noise to the weights. Okay. So basically, so what's the abstraction? We're saying, okay, I have my database, and the function that I'm interested in is the model weights. Let me think of this as my function. I start from my database X, and what I output is the model weights. Okay, this is some function. I'm releasing this information. And now I want to do this privately. Yeah. Yeah, we'll come. Yeah, exactly. So that's one, add noise to the weights, add noise to the training data. It's a little bit like randomized response was doing, right? Randomized response was adding noise to the training data. Laplacian mechanism was adding noise to the weight, right? Because you add weight noise to the output of the function. Okay. So the problem with both of these things is when you think of these models, they're actually very sensitive. Okay. Sensitivity of these models is pretty complicated, right? You know, if you think of this compute, what you're trying to compute here, it's not a simple function like the mean, right? You're doing some giant, like, you know, sophisticated optimization, and then you're outputting the parameters of that model, which could be a very, you know, sensitive function. Okay. So one clean abstraction or ideal thing you would like is somehow to do, well, at the beginning we said machine learning is empirical risk minimization. Right. So you have your data set, like, you know, x1, y1, x2, y2, so on. Okay, and this whole thing is x, really. Okay, and we have our parametric. Let me put a bar here just to distinguish it, that you have labels. Okay. So what do you do in empirical risk minimization? You have some parametric family of predictors, and then you try to find the parameters or the model weights which minimizes the loss, the empirical loss. Okay. You can recall this going back all the way to the first lecture. Okay. So this is what, you know, ML was for us, right? And what are we outputting really? In some sense, the ideal goal is to output theta star, which is argmin of L of theta. Okay. You start with your, like, you know, image labels, or you have your sentences or whatever you have, and you try and do this sort of model fitting. And so f of x bar, the ideal function is argmin. Let me put x bar here just so that it's clear. Okay. And this might be a very sensitive function. We don't really understand it as well. Okay. And the question is whether we can do something similar with privacy. Right? So that's what we want to do. And so there are ways to do this. There are 3 ways. You know, 2 of them you already mentioned. So first one is output perturbation. Okay, meaning you compute some theta and release theta plus noise. Okay, which was the first session. You compute the weights that you did, you know, however which way you were, whatever you were doing before, and now add noise. It's kind of okay, but in some cases for complicated models, this might not be a good thing, just because the sensitivity might be very high and you don't know how it really, how much noise you need to add. Okay. And unlike for the earlier questions where we studied privacy in the context of empirical risk minimization. So there is input perturbation. Okay, so perturbing the data set, even for computing the mean wasn't very good, right? Laplacian mechanism was much better even for the mean. So you can imagine for complicated things, it might be pretty harsh. Okay. So far, all of the things that we discussed are kind of falling into these two categories. Right? For empirical risk minimization, there are actually two additional things you can do. And these are specific to ERM, and if you want to do private ERM. And what are they? The first one is called objective perturbation. So what is objective perturbation? Well, let's look at what we are trying to do, right? So we are trying to minimize this loss function, this overall loss function, right? So we had, so we're trying to minimize L of theta as 1 over n. Okay. So objective perturbation says, don't try to optimize this exact function, but just add some noise to this. Okay. And then you compute, try to compute. Right. So the idea essentially is that by solving for this perturbed function, maybe you're, when I solve for this perturbed function, the answer is still good for the original function, but because I'm adding random noise here, maybe it doesn't memorize as much about the original data set.
Changes into the optimizer like that.
Yeah, so we are doing it here. So I mean, if you think of doing SGD, you are essentially adding some noise in each gradient computation, right? But the noise is fixed in the sense that in every gradient computation, I'm adding the same noise vector, right now at least. Okay, so that's a very good suggestion. Is like, if you think of this in terms of what it does to your training mechanism. So let's say I'm trying to minimize the loss by computing the gradient. The gradient essentially in each step now is the old gradient plus a noise vector, right? And that leads us to the fourth method, which is gradient perturbation. Okay. And gradient perturbation just means that you add noise to each gradient computation. Okay. In fact, this is called, there's a name for it. This is called differentially private SGD. So suppose I have my loss function. Okay. So the main method that we use for training such loss functions is to use SGD, right? Okay. So one thing I should say is objective perturbation could in some cases be more powerful than gradient perturbation as we are discussing below. Because maybe sometimes, the best way to optimize a function might not be just by the gradient. Maybe you have to do something more sophisticated, like maybe you're doing Nesterov accelerated gradient descent, or maybe you're doing something like multiplicative weights or mirror descent, or maybe using some more sophisticated, like interior point method, Newton's method, or whatever, right? So any of those would still be applicable for this new loss function. Okay, so our objective perturbation is kind of a more generic method, but at least in the context of many applications, gradient perturbation is perhaps more suitable, just because you're training based on computing SGD. Yeah. Right. The problem is it's very hard to quantify those things, especially when you have like very complicated models. Right. Like let's say I have 10 layers, then it's hard to quantify the sensitivity when I just say, okay, I change one weight, there are huge data sets, then grading the noise sensitivity might be pretty hard to just kind of empirically get a sense of it. People do try such things. The way people try to get a handle on this is by doing things like clipping weights and so on. Like you clip the weight to be at most something, and that kind of gives you some bound on the sensitivity. You're not exactly computing the sensitivity, but you get some control by saying no weight is going to be more than 100. Something is more than 100, I just round it down to 100. There are many other reasons why you do it, but you can see it can also help with privacy. Right? Okay. So if I'm trying to do SGD here, just recall, and then let's think of batch size being 1. You can obviously extend it to other batch sizes. You say I do something like this. Pick a random user and then set update the weights according to the gradient. Okay, so this is SGD. You pick a random example, update the gradient, update the parameters according to the gradient. Okay, so what should DPSGD be? If I want to make this differentially private, what would be a natural thing to try? Any suggestions? Yeah. Exactly. So here you add some noise. Okay. So I'm going to add some noise here. And let me say ZT. And it turns out that the right noise to use should be Gaussian noise. Okay. And this is a setting where the advanced composition theorem is critical because the number of iterations is huge. So a quadratic savings is like is very, very important. Okay. And you might wonder, okay, does this work intuitively? It's okay, because somehow you expect, right, deviate a little bit in the, at the beginning based on the gradient descent, I should still somehow be okay. Okay. Yeah. Right, exactly. So that's one way. But the other thing is that you might be using other methods to do the optimization. Maybe not SGD, you might be using like overall gradient descent or something else. Even if you're doing something else, objective perturbation is still a meaningful thing to do. Okay. Yeah.
So is step size important here?
Yeah, definitely. Step size is important. And in fact, you want your noise to scale accordingly, right? And typically when you do it in practice, you do gradient. This has to be done along with gradient clipping, right? So you do clip of the gradient. We call this GT. So clipping just means that if some, some coordinate has a huge value compared to the others, you do some clipping there. Okay. So in fact, there are sort of software packages that are available which can do this for you. One such one is Opacus. It just tells you, lets you train PyTorch models using differential privacy. And if you're interested, there's like, nice tutorials and everything. It's kind of explain what we went over in the context of training actual models. Okay. So for instance, if I want to, I have a model, I have some optimizer, I want to make it private. Now all I have to do is just kind of call this thing, and this will essentially, what will it do? It'll run a variant of this algorithm. Okay, it's going to add noise, but how much noise it's going to add and so on, it's going to do some auto tracking. It'll kind of keep in mind how much variance each coordinate has so far and so on, and then adjust the noise accordingly. Okay, but all of that is kind of inbuilt. So remember, as I've been saying at the beginning, since the beginning of privacy is only relevant when you have a proof that you have privacy. Right? You cannot demonstrate it empirically. Okay. So if I go out and say, okay, here I'm going to release this model, which, let's say a company has trained on, your emails, right? It's a lot of private information. I'm not releasing the data set, but I'm releasing the model for everybody to see. Okay. And that could be very bad. And if you want to do it really properly, then you might have to do it. So of course, for many, there's always a trade-off, right? If you want to do privacy, then your data set sizes increases for the same accuracy. Right? For some critical applications, you might do it. For some other things, you're more willing to lose on privacy for the sake of accuracy and so on. Okay. And in the next lecture, I'll say a few more words about differentially private SGD and some other privacy models, and then we'll jump to the next topic. Okay. And remember, assignment 3 is due today at 10 p.m.